Okay, so we've talked about a lot of transforms so far, and we have constrained them typically to um, L201. So we're just looking at that little range there. Now it's pretty obvious that if you have something that goes from 0 to 2, that you could just scale the time axis or the x-axis and use the same basis, or maybe scale the basis length by a factor of 2. So that's always an option. But often we want something that lives on a long time interval, and we would like to break it up into chunks. And we did this with JPEG, for example. With JPEG, we took a larger image and we broke it into 8 by 8 chunks. And then we used basis functions for those 8 by 8 chunks, and we built up the whole image by building up each 8 by 8 chunk and putting them back into the proper position like tiles, and that gave us the whole image. So let's see, I'm going to write this differently. Okay, so we want to represent a signal that might have some arbitrary length or extent. And we can do this by breaking it up into chunks and representing each one individually using our basis that's good over 0, 1. And then we build up the final signal as we did once again with the DCT. So to make this a little bit more precise, suppose that we had some basis on 0, 1. So psi k of t for k greater than or equal to 0 is an ortho basis. It could be just a basis, but hey, we've gotten so addicted to the wonderful properties of ortho bases that if we don't have one, we would do what we can to make sure we do. Okay, so it should be pretty obvious that for any integer n, psi k t minus n, the same basis, now just shifted, is an orthobasis on L2 and n plus 1. So let's define psi k comma n of t to be psi k t minus n. Given that, we have this beautiful result, which is that we started with a basis on just 0, 1, and now we have this for n is any integer, and k, as before, is an orthobasis for the whole real line. So now, any signal in L2 real line can be written as x of t. We're going to have a double sum because we have to go over both n and k. Like so. And we call this part right here our expansion coefficients. So these would be our alpha and comma k expansion coefficients. So, using this handy tool, now we can look at doing some analysis of the signal for all time. So if you've had any signal processing courses before, you've seen something like this already. The short time Fourier transform is what we use to get spectrograms, for example. And the short time Fourier transform is effectively divides a signal up into blocks, takes the Fourier transform of each block, and then if you want the spectrogram, you can plot the magnitude of those transforms at each instant of time, and you get an image. It's two dimensions. You have your time offset, your block offset, which corresponds to n in this particular case, and then you have your frequency, which corresponds to k. Now there are a few subtle differences. One of those is that with the spectrogram, we often have the blocks overlapping, but here the blocks aren't overlapping. Is I guess the main difference. Okay, so I've added just a little bit more text here. One of the ways to look at things is down here, is that when we are representing our continuous time signal with this discrete set of coefficients, we actually, as described before, we can view this as having two indices. One's a time index, that's our n, and the other is what we typically think of as a frequency or vertical index. So I think one of the miracles in mathematics is that we have a continuous time signal. It's uncountably infinite, and we only place some limited constraints on it, that it can't be infinite, that it's in L2, and we can now represent that signal with a doubly countable infinity of coefficients. So it's a pretty remarkable change here. Okay. Here's an example using the DCT basis. So over here we have the DCT basis, and you'd recognize that as being in one column. But we now have a grid because we have time on this axis, and they're exactly the same, they're just shifted in time. And we have frequency on the y-axis, starting at lowest frequency at the top, higher frequencies as we go down. So if we took some signal like the one over here on the right, where I've written x of t, looks like we've got a pulse of a pretty high frequency and then a slightly larger pulse of a lower frequency, and we run it through this transform, this DCT, and to get the expansion coefficients, we get something like this. So you can look at the time axis here. It's a little bit small, and I apologize for that, but each one of those ticks is one sample in time, or one unit of time. So we have -4 to -3, -3 to -2, and so on. So we can represent the first part, and it tells us we've got a little bit of this frequency right here. And then as we get more into the signal itself, we start to see the signal gets stronger and really strong, and then it fades out. And then we get over here to this other lower frequency pulse, and now we have lower frequency index because we're higher. So in this case, 0 frequency would be at the top, and the highest frequency would be at the bottom of this chart. So it's upside down from what you might be used to thinking of with your spectrogram. Incidentally, the MATLAB spectrogram now uses this upside down view. It's upside down to me by default. Now, let's assume that we did some approximation, and actually maybe this isn't the best venue, so I'm going to let you, actually we can go back to it with our image compression example here. Over here on the far left one, we can see we have little squares making up our image. And when we move to the next one, I'll try to zoom in a little bit. You can still see the squares. Each of the squares tends to have some shape to it. It's got some of the image there because it's got several of the coefficients. But there's always a break at the boundaries. You can see where the squares are. So that's often a problem. And in the next lecture, we're going to look at a way that we can avoid that type of a problem with block transforms. So if everything's fine and everything's perfectly represented, this problem does not arise. But if we perturb any of the coefficients, then at these boundaries, at these integer boundaries, the signals that are built up in their separate integer cells won't match at the boundaries. And when you look at an image that's that way, you can see the blockiness. And when you listen to something that's built up that way, you hear a buzz or a click, depending on how wide the block is that you're representing with each transform. So it's a big problem, and we'll see that there is a way to gracefully, if you will, blend these edges together.